We all exist in an energy field that naturally expands and repels itself. It is natural because the expansion lowers the field's energy density and stress, and increases entropy. The figure shows a two-dimensional depiction of this field. The arrows represent the outward expansion, and the gray shading represents the field's energy density. Only the atomic nuclei can interact with and displace this field. Each nucleus creates a tiny energy void. A planet, like Earth, is simply a vast collection of these voids. Together, they form a spherical zone of reduced energy density and reduced expansion repulsion. In the illustration, this reduced energy zone is shown as the lighter gray region. Gravity, in the Earth example, is the result of this reduced repulsion zone being completely surrounded by an unimpeded field. Mass is not an intrinsic property of matter. It instead emerges from how nuclei displace the substrate and how the substrate resists forced acceleration. This resistance, or pushback from the substrate, is what we call inertia. Orbits, trajectories, and freefall are all undefined without adding an additional energy displacement zone, or mass. Start with a simple two-body system. Each body creates its own repulsion impedance zone. This zone is a cluster of energy voids surrounded by an unimpeded field. Outside the control volume of the two-body system lies the entire universe of unimpeded field. Unimpeded field also exists between the two bodies, but the full repulsion push on each zone is blocked by the other. The result is a mutual push toward one another. In a real multi-body system, the field is filled with zones of varying size, density, and distance. This produces a complex but geometrically precise three-dimensional field mediation, where free-fall motion naturally takes the form of a trajectory. Does gravity attract? Do two bodies pull on each other? Actually, no. Where does gravity control fit in? Gravity control gets labeled as fringe science, yet the term negative mass has been a respectable physics topic for a century. But you don't need to invent a new term or imagine an exotic material. You only need to create a high impedance zone or an otherwise high effective mass without using dense nuclei. Place that higher impedance zone directly above the cargo mass and let the universe do the lifting. Earlier, I mentioned inertia, a stiff resistance to an external acceleration on a mass. But why does the field resist acceleration? And does the field or substrate have stiffness? The field isn't physically stiff, the way steel is. The stiffness comes from something deeper. Fundamentally, it must simply resist rapid changes in its own configuration. That's it. That's the key. A pure energy field cannot resist steady motion, so it has no way to care about velocity. But a change in velocity, or acceleration, that's a change in field configuration. So if a collection of field voids, matter, is forced to accelerate through the energy field, the field must reconfigure itself. That reconfiguration costs energy, and the field pushes back. That pushback, the inertial force, emerges naturally from the stiffness of the field. The planet Mercury has a perihelion precession. Simply put, it wobbles a little in its orbit. Newtonian mechanics can account for about 92% of the precession due to perturbations from other planets. But the last 8%? That was a nagging problem for astronomy for over 50 years. Fortunately, Einstein's general relativity solved the problem by adding a geometric correction. As Mercury moves in its elliptical orbit, it samples regions of slightly different space-time curvature. That asymmetry accumulates and rotates the orbit. But would an energy substrate be able to provide a similar correction? Yes, a field stiffness correction. In the substrate model, the substrate is compressed more strongly at perihelion than aphelion. The stiffness of the medium responds asymmetrically, adding a tiny extra inward bias that accumulates and rotates the orbit. Everything so far has described the gravity substrate mechanism. Can that same mechanism explain dark energy? After all, dark energy is an energy field. Next, by adjusting the dilution factor, the coupling behavior, and the relaxation dynamics, we will explore the mysterious and elusive dark energy. In the standard cosmological model, dark energy is treated as a constant energy density filling all of space. As the universe expands, its total amount increases, but its density does not change. There is no provision in the model for how this energy is replenished. In the figure, The lambda cold dark matter curve is fitted to type 1a supernova data. 3 parameters are required to make the observed redshift data fit, and they are shown in the plot legend. But if we acknowledge that a constant density field expanding without dilution implies a missing mechanism, then fusion loading may supply that mechanism. The next figure shows the same supernova redshift data fitted with the substrate energy model. Only a single parameter, the exponent governing substrate evolution under fusion loading, is needed to match the data. How does a 1-parameter data fit compare to a 3-parameter fit? The next plot has both curves plotted together. The blue dashed line is the current standard model. The red solid line is the energy substrate model that uses fusion energy replenishment. Can you see any difference? By now, you're probably wondering what comes next. We've seen that a substrate with stiffness can explain gravity, inertia, Mercury's precession, and even the redshift story. So the natural question is, can the same medium also account for galaxy rotation? In other words, can a substrate with stiffness generate an angular momentum response strong enough to remove the need for dark, non-baryonic matter? In the figure is the galaxy rotation curve for the M33 galaxy. In this plot, you will see the observed data, black dots, the Newtonian model, blue dashed line, and the universal substrate response, red solid line. As you can see, the substrate response is able to predict the galaxy rotation profile very well. The next figure is another galaxy dataset, UGC128, with the substrate stiffness response applied. On the grand scheme of things, this is a good fit. For a reference failed fit, just look at the blue dashed line for the Newtonian curve. Note the model, applied to 2 different galaxies, have not been individually tuned or cooked to fit. For decades, astronomers looked at galaxy rotation curves and said, "This proves there must be dark matter, invisible, non-baryonic mass surrounding every galaxy." That was a bold claim. It wasn't presented as a possibility. It was presented as a discovery. I'm not going to make such a claim here. I am simply showing that a mechanical response of an energy substrate, with no tuning, no halos, and no exotic particles, can track real galaxies surprisingly well. So what do you think? Please leave a comment. I would love to hear from you. And of course, if you made it this far, please leave a like.